Okay, so our objective today is we've talked about how to figure out the areas of basic shapes, but what if we have a pentagon or a hexagon or an octagon or something like that? There's no formula for each one of them. So, and I could not figure out the area of every kind of shape, but if I have something that is regular, predictable, meaning all the sides would be the same, all the angles would be the same, then I could actually come up with a formula for that. So that's what we're going to work on today, is to understand, bless you, the formula for the area of any regular polygon. And because we're in math class, you cannot look at that word regular and think of an English idea behind it. So we're from lesson 11.4. So I'm going to write this down. This is not a vocab word because it's already been a vocab word. Because I've had this idea on several different quizzes and tests, and people still persist in getting it wrong because they don't understand the definition. So a regular polygon is a polygon, oops, whose sides are congruent so don't write this as a vocab word. You already have it. It's not part of this chapter. And whose angles are congruent. So it's a very special polygon. And it's due to its special nature that we're able to do anything with it. And we, just like with that isosceles trapezoid, it gave us freedom to solve problems that if it was a regular trapezoid, we could not. Okay? So I'm going to give you some real vocab that you need to understand that deal with regular polygons. So if somebody talks about the center of a regular polygon, what they mean is the center of the circle circumscribed about the polygon. So the center of the circle and the center of the polygon are the same value. Okay. Then we have what's called the radius of the regular polygon. Oh, a miracle occurred. We now have full juice. Weird. And that is the distance from the center to a vertex. Now, let's use a little bit of logic on this one. For something to be inscribed in a circle, a shape, what has to be true about the vertices of that shape? Dakota? Has to be touching the edges of the circle. So if the radius of a regular polygon goes from the center of the circle to the vertex, what could you say is true about that radius? Drake? Yes, but that's not really what I was looking for. Thomas?
It's also a radius to the circle.
It would be the same as the radius of the circle. Okay, so keep that in mind. I'm going to go to the next slide. Everybody ready? So the next vocab word is going to be the central angle of the regular polygon. and that's going to be an angle formed by two radii drawn to consecutive, so one right after the other, vertices. So implicit in the notion of radii is that it has to come from the center of the circle. So a central angle of a regular polygon starts at the center, two radii to adjacent or consecutive vertices. And I'm going to draw a picture of all of these so that you can see it. Now here comes the weird one. This one I don't think you've ever heard before. This one is called an apothem. Always makes me think of Batman. I don't know why. Apothem of a regular polygon. So an apothem of a regular polygon is the perpendicular distance from the center of a polygon, aka the center of the circle, to a side. Not to a vertex, but to a side. Okay, so let's get a picture of this. Okay, what shape did I just draw? Okay, so A, B, C, D, E, F, G, H, O. So O is the center of the regular, and I'm going to just tell you it's a regular octagon. So you have to trust what I'm telling you, not what it looks like. A, B, C, D, E, F, G, H. Okay? Josiah.
So would a pop-up be similar to like a tangent?
Okay, no, it will not. Okay, I'll draw a picture and you'll see in just a second. Okay, now I'm going to draw some pictures and we'll label things. So this dashed line, segment OE, is the radius of the regular octagon. And angle AOB is a central angle of the regular octagon. Aiden, you need to take notes. Ethan, you're not writing anything. So what the heck is that apothem? That apothem drops down from a radius perpendicular to a side. And we'll give a little letter there, we'll call it X. And segment OX is the apothem. So notice that it does not go to a vertex, it goes to the center of a side. What kind of little triangle do I have right there? I have an isosceles triangle, okay? So there's a lot of math I can do if I have an isosceles triangle. Drake. Correct. Because where the circle would meet this octagon is at the vertices, so it is not a side, so that would not be a full radius. So we can't just say, oh, easy. No. If that was the case, we wouldn't even need what we're going to be talking about. Okay? So, knowing all this now, everybody good with the diagram? Oh, hold on. All right. We have a theorem that goes with this notion of apothem, because remember I told you you had to know the formula for the area of a regular polygon, and all we've talked about is regular polygons. Well, here it comes. Theorem (11.6) states the area of a regular polygon, so it doesn't matter how big it is, as long as it's regular. So a square is equal, but we have a better formula for the area of a square, to half the product of the apothem and the perimeter. In other words, A equals, so capital A for area equals 1/2, and apothem, by the way, is a little a, and P stands for perimeter. Okay. Now, sometimes, because this is a brand new notion, they're going to give you the two key pieces, and your job is to figure out the just the area, and you just plug and chug. Most of the time, you're going to have to figure out something, whether sometimes it'll be the apothem you have to figure out, sometimes it's going to be the perimeter. Okay, so let's do an example. Directions are going to say find the area of the regular hexagon. With apothem 9. Okay, so we draw a hexagon, and we need to remember some things about a hexagon. Okay. We can figure out what the angles all equal in a hexagon. Okay? And we can figure out that, remember how it works? We've got the number of sides, take away 2 times 180. That's going to give you 4 times 180, which is going to give you 720. Now, I have 6 angles that add up to equal 720. So I get that each angle of my hexagon is 120 degrees. Now, I'm going to tell you hexagons show up a lot. Now, when I drop a radius down, I've just split that angle. I've just bisected it. So what I've done is created a 60-degree angle. Now, by the way, that's a radius of the shape. When I drop down the apothem, which they told me was 9, I form my right triangle. And I didn't form any kind of right triangle. I formed a 30, 60, 90 right triangle. Okay, that's crucial. Now, 9 represents the long leg. What I need to do to figure out how long the side is I need to figure out what the short leg is and double it. So I'm going to use S here for this piece. And so remember how it works? The long leg is equal to radical 3 times the short leg. So I divide both sides by radical 3. That gives me S equals 9 over radical 3. I rationalize by multiplying top and bottom by radical 3. That gives me 9 radical 3 over 3, which gives me 3 radical 3. Now that is not the length of a side. That's half of the length of the side. So the side of the shape is going to equal 2 times that, which is 6 radical 3. But the formula wants me to know the perimeter of the shape, and there's 6 sides that measure that, so I have 6 times 6 radical 3, giving me 36 radical 3. So the area, which I'm cramming down at the bottom here, is 1/2 the apothem, which was the 9, times the perimeter, which was the 36 radical 3. So I can take half of the 36, which is 18, and I'm going to take this calculation and move it over here. And 9 times 18 is going to give me 162 radical 3. That is your area. Okay. Look at all the different chapters that got involved in that problem. Okay. Chapter 8, Chapter 9, along with the formula from Chapter 11. Okay. We're going to run out of time, but I'm going to be honest with you. Not all your shapes allow you to get an angle that is 30, 60, 90, or 45, 45, 90. So that means you may be using some trig on your homework as well. So keep that in mind. Okay? And I'm going to stop here.